All right, in this video we are going to cover hexadecimal numbering systems. Hexadecimal numbering system, or the hexadecimal numbering system. In previous videos we've covered, done a brief overview of numbering systems in general. In the last video we covered binary numbering systems. We did a little bit of conversion from decimal to hexadecimal, or I'm sorry, to binary and then to hexadecimal. We're going to do a little bit more of a deep dive into hexadecimal with this particular video. So the first thing I want to do is review the base structure of the hexadecimal numbering system. So we use the same values as we do with our decimal numbering system: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But we also add some letters here that represent 10, 11, 12, 13, 14, and 15. A, B, C, D, E, and F. So that is 10, 11, 12, 13, 14, and 15, which gives us the values 0 through 15, or 16 symbols to use to quantify whatever it is we're discussing or talking about. In this particular scenario, we're going to use the hexadecimal system quite a bit, in particular with IPv6 and the numbering convention with IPv6. All right, so we're going to start out with a value. We're going to start out with a decimal value, actually, of 735. Just kind of a random value that we chose, and there's a reason for that. We are going to draw out 1, 2, 3, 12. I believe that should do it. Okay, so we've got here 2 to the 0, 2 to the 1, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. Whoops. Looks more like 27, so 2 to the eighth, 2 to the ninth, 2 to the 10th, and 2 to the 11th. Now, if we calculate these values, in other words, if all of these bits that we have represented up here were turned on, what would these values become and how would they add up? Well, 2 to the 0 is 1, 2 to the 1 is 2, this is 4, 8, 16, 32, 64, 128, 256, 512, 1024, and 2048. Now notice again, we're dealing with a binary system here. Everything simply doubles as we go up. Makes it very convenient to work with. What we're going to do when we get to the conversion process, though, is we're going to divide these up into 4-bit segments. Okay? And we're going to deal with them individually. So they're not going to go up to 2048. This would be if we were using every single one of these. We're going to break them up into 4-bit segments. And so that's how we're going to look at this right now. If we look at that value of 735, it is less than 2048, and it's less than 1024. But it's higher than 512. So what we could do is we can turn these bits off and we can turn that one on. We'll take that value and we begin to subtract 735 minus 512. And that's going to give us a value of 223. And we notice that our next value is 256, which is larger than this. So we can't use it. We're going to turn it off. But the next value is 128. We can use that. We're going to subtract that, 128. And when we subtract that, that's going to give us a value of 95. Our next value in the bit segment here, 2 to the 6th is 64. We can use that. We can subtract 64. And that is going to give us a value of 31. We'll bring that up here, 31. Our next value is 32. It's larger than this, so we can't use it. But we can use the 16. We'll turn that bit on. That's going to give us a value of 15. Well, just a little shortcut here. We realize that all of these in this last 4-bit segment here add up to 15. So we're just simply going to turn each one of those bits on. Now we could do the math if we wanted to, but there's no need. We realize that those add up to 15, and it gives us the value that we need. So we just converted this to binary, which we've done in previous videos, but it's useful to look at how we migrate across these various numbering systems. So what we're going to do now, we're going to break these up into 4-bit segments. And we're going to do this for the purpose of converting to this hexadecimal value. Because what we realize is that 2 to the 4th equals 16. So each one of these, if we break them up and work with them independently, it gives us our hexadecimal base. Makes it easy to work with that way. So this is going to be 2 to the 4th, which is 16. This is 2 to the 4th, and this is 2 to the 4th. So what we realize here in that case is that this bit is turned on, and that is 2 to the 1. And if we look back here at our values, we see how that comes out. 2 to the 1 is simply going to be 2. So that value is 2. This value, 2 cubed, 2 squared, and 2 to the 0, and that is going to give us 13, and that equals D. And here, all of these are turned on. So that's going to give us the value of 15, which we know is F, or 15. So our hexadecimal value for 733, or 735, is 2DF. So what we've just done is we've converted 735 to 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, and then to hexadecimal, which is 2DF. Once you get used to working with these values, very easy to go from one to the other. This will give you a good snapshot and a little bit of a deep dive into the hexadecimal numbering system and the conversion process from decimal to binary to hex, and we could go back if we wanted to very easily.